Hello and welcome to the Unit 2 video, or one of them. So Unit 2 can be called a couple of different things. We can call it biomolecules, macromolecules, organic compounds, and of course we could say organic macromolecules or organic biomolecules. Or we could just say this is the chemistry of life. So this is looking at the molecular level, like think of molecules as being made up of atoms, of what makes up our bodies. So basically we're starting at the smallest level of organization, above an atom. So the nature of matter. Everything in the universe is made of matter. Matter is anything that occupies space and has mass. Mass is the quantity or amount of matter that an object has. So inside the object, it's how much matter or how many atoms are in that object. It's important to note that mass and weight are not the same. Weight is affected by gravity. If you're on the moon, your mass is the same, but you would weigh less because there's less gravity on the moon. So that brings us to the basic unit of matter, the atom. The atom cannot be broken down by any kind of chemical means. You have to get very complicated to break down an atom. So it's not going to happen chemically. It would have to happen physically, and you'd have to have some very expensive, fancy equipment to do that. Atoms typically have the same amount of protons, neutrons, and electrons. So if they have one electron, they will also have one proton and one neutron. And they're considered neutral. So they don't have more of a charged particle compared to the other. So if the atom has 4 electrons, then it's safe to assume that it has 4 protons and 4 neutrons, unless you see a charge attached to it or an extra number attached to it. And we're going to talk about how that'll happen in a few minutes. So matter consisting of atoms of the same type is called an element. So inside of an element is also known as a pure substance. Inside of an element, you might have 342 atoms, but all of the atoms are the same element. All of the atoms are, let's say, let's just go with hydrogen. And so they're all hydrogen, so they all have 1 electron, 1 proton, and 1 neutron, because that's how many hydrogen has. So there are 92 that are naturally occurring elements. 26 of those occur in the human body. So if you look down here, we have a picture of an atom. So here we have the nucleus, and there are blue particles and green particles. The blue is going to be protons, which have a positive charge, so I like to write P plus for positive. Neutrons have no charge, so they are neutral. And so the nucleus is positive because they're made up of positives and neutrals. So the nucleus is positive in atoms. Now the electrons float around and they're constantly moving in these shells. Okay, so electrons are negative, so I like to write them as E minus. So that brings us to the subatomic particles of an atom. Okay, so sub means below, atomic, atom. So as far as pertaining to an atom, these are below the level of an atom. So these are the things that make up atoms. So again, you have protons, which are positive, neutrons, which are neutral, and these make up the nucleus. And this is where the bulk of your mass comes from in an atom. because protons and neutrons weigh, or they have a lot more mass compared to electrons. Weigh would not be the correct term because it's mass. But anyway, so electrons are negative, and they are around the outside of the nucleus in the electron cloud. So if you look here, you see these pictures of atoms, and you see how they are doing like this. This is supposed to show that the electrons are constantly moving. So it's hard to show that. You see how busy it looks? So it's very hard to show that in a still picture, in a 2D picture like you have here. But just know that those electrons are constantly moving, and they are just floating around. So electrons are located in energy levels, and the energy levels are in the electron cloud. So that's where they move. The attractions between the positive in the nucleus and the negative of the electrons keep the electrons around that nucleus. And the outer shell is called the valence shell. So we're only going to learn up to the first 3 levels. It does go higher. So you need to know 2, 8, 18. The first shell can hold up to 2. Once it gets 2 in it, then it moves to it fills up the second shell. Once it gets the second shell full, so that would be 10, because 2 plus 8 would be 10, then you would move to the third shell. So in drawing an atom, I'm just going to put a dot for the nucleus. So if this is my first shell, I would have, this would be hydrogen. It only has 1 electron. This would be helium. It has 2. Okay, so that's a full outer shell because it only has 2. Okay, this makes it a stable element or stable atom because it has a full outer shell. If it does not have a full outer shell, so let's say we add a third one, then it's unstable. It's going to be more likely to bond with another atom. So that's going to come into play later. So typically you would draw the electrons paired up. So this would be 6, 2 in the inner shell, and then 4 in the outer. This would be 8, 2 in the inner, and 6 in the outer. And this would be 10. So if you look, we have a full inner and full outer shell. So again, here is a stable atom. Then if I needed 11 electrons in the atom, then I would draw another shell. You get the picture? So lithium has 3 electrons. So it has 2 in the first shell and 1 in the second shell. And I just drew lithium a second ago. Valence electrons are the number of electrons present in the outermost shell. So lithium had 1. So it has 1, this atom has 1 valence electron because it only has 1 atom in the outer shell. This one has 2 valence electrons. So atoms with the same number of valence electrons have similar chemical behaviors. And if it has a completed or full valence shell, then it is considered non-reactive. Okay, so it is stable. It's not going to readily react with anything. If it has an incomplete valence shell, then it is considered unstable, and it is more likely to be reactive and more likely to bond with other substances. So in this case, lithium is going to bond with other substances more readily than, say, helium would, which has a full outer shell with only 2 electrons. So the number of protons in the nucleus is called the atomic number. It is written as a subscript. So it's to the left of the symbol. So that's the number of protons. The total number of protons plus neutrons makes up the atomic mass, or mass number. Okay, so remember how I said protons and neutrons make up the bulk of the mass? So that would be in the nucleus of the atom. Electrons are teeny tiny, so they really don't contribute to the mass. They are 1/2000th the size of protons and neutrons. So their mass is really negligible compared to a proton and neutron. So atomic mass is the sum or total number of protons and neutrons. And so it's written as a superscript. So an example here would be 12. So oxygen has 8 electrons, so that means it has 8 protons, and it also has 8 neutrons because you should have the same amount. So its atomic weight would be 16 because the atomic weight or atomic mass is going to take into account both protons and neutrons. So this is the periodic table of elements. You'll study this much more in depth when you get to chemistry. But for now, we're just going to introduce it to you and take a look at it because we are going to be talking about some of these atoms. So if you'll notice, it's color-coded. So you have column 1. I don't know if you can see the 1, but all the red things are going to be your alkali metals. There is a mistake here in the notes. This should say column 17. 17 is your nonmetals. And then you can't see very good because of my app, but the purple here is going to be your noble gases. Okay, so anyway, the noble gases, if you look, 2, that's a full outer shell. 10, that's a full outer shell. 18, that's a full outer shell. So one of the things that the noble gases are known for is being non-reactive because they have full outer shells. So anyway, that should be 17 and 18 on the bottom here where you fill it in. Please make that correction. So each element has a very unique symbol, and it's usually the first 1 or 2 letters of the name. This is usually from Latin or German names. Most of them are Latin. But there are 4 elements that make up 96% of the human body, and that is CHON. You can remember that by CHON. Carbon, hydrogen, oxygen, and nitrogen. So carbon, hydrogen, oxygen, and nitrogen, CHON, make up 96% of the human body. So if you look, there's CHON, and then below that, here's lots of other things too. So you might recognize some of these: calcium, phosphorus, of course sodium. We take in a lot of sodium, iron, if you've ever heard of anemia. So anyway, these are all things that our body takes in, but in smaller amounts. So an isotope, so that's isotope. I'm going to write it over here, isotope. An isotope is an atom of an element, and it has the same number of protons, but it has a different number of neutrons. Okay, most isotopes are considered unstable, and they tend to break down to become more stable. And when that happens, they release radiation. Now, I'm not sure if everyone knows this about me, but before I was a teacher, I worked in radiology. I did x-rays and MRIs for a living. And in going to school, of course, you know, it's 2 years of school where you're learning about radiation. MRI does not emit radiation, but X-ray does. So we had to learn a lot about that and take a big test and all that jazz. So anyway, radioactive isotopes are, you know, given to some patients. My husband, he also did radiology. He did x-ray, but then he went into nuclear medicine. So I chose MRI because MRI is way more interesting. He chose nuclear medicine. In nuclear medicine, they actually give you radioactive isotopes. So they might inject it into a vein, or you might even eat it. But you're taking in radiation into your body, and then the radiation comes out of your body and hits a detector, and that radiation is tagged to a specific organ. So anyway, isotopes are atoms that have the same number of protons, but they have a different number of neutrons. So if you look down here, you have carbon in the picture. So regular carbon has 6 protons, 6 neutrons, and 6 electrons. So that's normal carbon, neutral carbon. Carbon, it can be radioactive. So carbon-13 has a different mass number of 13 because it has an extra neutron. Now, it is still neutral because neutrons are neutral. So it still has 6 protons that are positive and 6 electrons that are negative. So that it has an equal number of positives and negatives, but it's an isotope because it has a different number of neutrons. That makes it heavier. That extra neutron makes it a heavier atom. And then you also have carbon-14, which adds even more neutrons. So that makes it even heavier or way more mass. So, like I said, most carbons are the normal carbon. They have 6, but you get into radioactive carbon, and you will talk more about that next semester when you're talking about relative dating and radiometric dating of fossils. This is how they can kind of say that, okay, well, this dinosaur fossil, whatever it is, if it's a pterodactyl, it would have lived X amount of years ago, because they can look at the radioactive carbon and they know how long it takes to break down. So my husband, what he used to do, one of the most common radioactive isotopes he used has actually a relatively short half-life of 6 hours. It's called technetium. And so they would inject that into the person, and then in 6 hours you can expect for it to have broken down by half. That's what half-life is. And so they would have to calculate the dose based on what time the patient was to get there, and if they needed to stay there for a certain amount of time. So anyway, radioactive isotope. So atoms can bond. If you do not have a full outer shell, then atoms are going to lose, share, or gain electrons. Somehow, some way, they're going to attempt to become stable to get a full outer shell. So the goal of bonding is having a full outer or valence shell. So that's the goal of bonding, okay? And if they need to lose electrons to do that, gain electrons to do that, or share electrons, then they will do that. So every atom has a specific total number of covalent bonds it can form, and that depends on how many unpaired electrons you have. So that's called the valence. So the valence of hydrogen is 1, because if I'm drawing a hydrogen atom, hydrogen has 1 electron. So it has 1 open spot. Carbon has 6. So it has 2 in the first shell, then 4 in the second shell. Now, if you recall, that second shell holds 8. So it has 4 openings in its second shell. So carbon is extremely important because it can covalent bond with up to 4 different things, because it has 4 different openings, which is why carbon is very prevalent for living things. So an atom may also combine with itself. 2 hydrogen atoms might combine to form H2. So another example of this is O2. O2 is the oxygen you breathe in. You cannot breathe in O1. You cannot breathe in O3. O3 is ozone. O2 looks like this. Here's my nucleus, my inner shell, my second nucleus, and my second inner shell. And then what happens is the first one, oxygen has 8. So the first one will have 8 electrons. And so 2 will be shared. 2 will be shared with this other atom. And this other atom also has 8. So that means it'll have 6 in their outer. So they have, this one on the right has 2 openings. This one on the left has 2 openings. So they both need 2, so they share 4, if that makes sense. So that's O2. Atoms may also combine with other atoms to make a compound. So water and salt are examples of compounds. So when pure sodium and chlorine combine, they form salt. I don't know if you knew this or not, but sodium is a metal. Chlorine is a poisonous gas. Both of those are dangerous to you. But when they combine, they have an emergent property because they change the characteristics, and now they're totally safe. So that's kind of cool. A compound is a substance made of the joined atoms of 2 or more different elements. So there's not 23 types of bonds. There's 3. Sorry. There's 3 types of bonds that we're going to learn about. So a force that joins atoms is called a bond. So we're going to talk about covalent, ionic, and hydrogen bonds. Ionic and covalent bonds are most similar because they both fill the outer electron levels, and that is in order to stabilize the atom. So remember, the goal of bonding is to fill those outer electron levels to become stable. So covalent bonds are created when 2 or more atoms share electrons. Okay, so I always teach my kids, and this will help you remember, sharing is caring, and caring is covalent. It's a silly saying, but kids always remember it. So I think we all know sharing is caring. Caring is covalent. So anyway, this is usually not metals. So hydrogen has 1 electron in its outer shell, so it's going to readily share that 1 electron. So a lot of molecules have hydrogen that are sharing the electrons. Molecules are held together by covalent bonds. Some examples of that are water, carbon dioxide, that's ammonia, methane, different atmospheric gases, oxygen, nitrogen, hydrogen. All organic compounds are held together by covalent bonds. That's a very important statement. All organic compounds are held together by covalent bonds. Okay, organic compounds are the primary thing these notes are about. So that's your carbohydrates, proteins, lipids, and nucleic acids. Those are your organic compounds, and every single one of those has covalent bonds. So this is a covalent bond. I know it's a covalent bond because right here they are sharing. If you notice, the lines, the shells, the outer shells are overlapping, and they are both sharing these 2 electrons. So to draw a covalent bond, I'm going to draw water. I've already drew O2. So let me just show you the breakdown here. Water is H2O. Hydrogen has 1 electron. Oxygen has 8. Okay, but there's 2 hydrogens. So my water molecule should have 10 total electrons. And this is just stuff that I know. You're not going to be asked to draw any atoms, but it just helps you understand. So I'm going to start off with my oxygen. Here's my little nucleus, and I'm not an artist by any means. So I have 2 electrons in the inner shell for oxygen, and then 6 in the outer. So these are my hydrogens. Okay, so hydrogen has 1 electron. So there's only one place for it to go. It's going to share its 1 electron. This is my first hydrogen, and here is my second hydrogen. Now, to make hydrogen happy, it needs 1 more electron. So oxygen is going to share 1. So now this hydrogen on the left is happy. Oxygen is going to share 1 with this one. Okay, and then oxygen has 6 total. Okay, so the green is oxygen, so I have 1, 2, 3, 4, 5, 6, and then hydrogen has 7, 8 that it's sharing. So on the bottom here, you have 8 total electrons being shared. Can you see the 8 electrons being shared? And so that makes this atom happy. And then here, hydrogen has 2. Okay, so what this does, I'm going to go ahead and show you something called polarity. Now, what did I say was in the nucleus of atoms? Protons and neutrons. So in this nucleus up here, I've got 1 proton and 1 neutron. So what's the charge? Should be positive because neutrons are negative, right? So we're going to have a positive charge. Same here, positive charge. If you look below this line, there are no electrons, so there's no negatives. So this is an unequal distribution of positives and negatives. So if you're looking at water like Mickey Mouse, then Mickey Mouse's ears are positive because all the electrons are around Mickey Mouse's face. So this oxygen has eight protons in its nucleus. But if you count, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons below this line. So that makes Mickey Mouse's face negative. So this is an unequal distribution of electrical charges. And that's going to be important for something we're going to talk about later. So that brings us to molecules with an unequal distribution of electrical charges, like water, which we just drew, are considered polar molecules. So water has a positive charge on one end and a negative charge on the other. So again, if you're looking at Mickey Mouse, the ears would be positive and Mickey Mouse's face would be negative. So because of this uneven charge, water is considered polar. So what happens with polar molecules is they tend to stick together. So if you look at this picture down here, and you have the reds are Mickey Mouse's face, so they're negative. And then the ears are positive. Then the negative is going to stick to the positive. So this negative face is going to stick to the ear, the positive ear here. Same thing here. So this causes water molecules to stick together. This bond here between these polar molecules is a hydrogen bond. So this is a weak bond that can be pretty easily broken, but a hydrogen bond is between polar molecules, and one example of that is water. Many water molecules. One water molecule, how the ears stick to Mickey Mouse's face, would be covalent, but when you put many water molecules together, that would be a hydrogen bond, where the positive sticks to the negative. So, again, if I want to draw a hydrogen bond, I'm not going to draw all the electrons. I have Mickey Mouse. So we have two water molecules. So what's going to happen is the positive end will stick to the negative end. So here is your hydrogen bond. So this is why water sticks to water. This is why water puddles. This is why water also sticks to other surfaces, like it might stick to the outside of your water bottle with condensation. Lots of properties of water can be tied back to these hydrogen bonds. Now, if you recall, covalent bonds are the bond between the hydrogen and the oxygen. Those are the covalent bonds. But between more than one water molecule, that is your hydrogen bond. So ionic bonds are formed by the electrical attraction between oppositely charged ions. So what that means is a positive and a negative. So an ion is simply a charged atom. How you can become a charged atom is by gaining or losing electrons. Okay, so you become an ion by changing your number of electrons. So if you recall, you become an isotope by changing the number of neutrons. You become an ion by changing the number of electrons. If you change the number of protons, it becomes a totally different atom. So we don't talk about that. So ions have an electrical charge because they contain an unequal number of electrons and protons. So if you lose electrons, remember electrons are negative. So if you're losing electrons, then you are now positive because you lost negativity. So you're now a positively charged ion. If you gain electrons, and again, electrons are negative, then you're gaining negativity. So now you have a negatively charged ion. So ions tend to interact to form an ionic bond because the positive ion will stick to the negative ion. And typically this interaction, one atom needs an electron and another atom needs to give one away. So it kind of works out for both. Usually this occurs between metals and nonmetals. One example of this is salt. So sodium plus chlorine gives you sodium chloride, which is table salt. So down here you have a picture of an ionic bond. So this is sodium and chloride. So if you see, sodium becomes positive because they give away an electron, and chlorine becomes negative because it gains an extra electron. So to form table salt, the single electron, so sodium only has one electron in its outer shell, becomes pulled away, and then that completes chlorine's outer shell. It has 7 electrons in its outer shell. So it needed one more, so it just took it away. And that benefited both atoms. So when you have a negatively charged electron that is lost, you're losing negativity, so then it becomes positive. Okay, so if you lose your negatively charged electron, you're now positive. So what we do is we add a little plus sign at the top. So a little plus sign like where an exponent would be. So that's called a superscript. It's hard to get that to type in, so it didn't show up very well here. Anyway, so then the element is considered a positive ion. Another name for a positive ion is a cation. So you can remember that by C+. Chlorine, like we said, has 7 electrons in its outer shell, and it's going to strongly attract the electron from sodium because it needs one more electron. So when the electron is gained, you're gaining negativity. So then it becomes a negative ion. And same thing, you would write it with a superscript, like an exponent. So a negatively charged ion is also called an anion. Okay, so you can remember that by saying A minus. So A minus or C plus, what do you have? And again, a hydrogen bond is formed when hydrogen is attracted to 2 other atoms, usually oxygen or nitrogen, and they're very weak, and it's going to occur between the polar molecules. So, ionic bond. I'm going to draw you a very simple ionic bond. So, if we start out with hydrogen, which has 1 electron. Okay, so hydrogen, it has 1 proton, 1 neutron, 1 electron normally. Okay, so how many does it need? It needs 2. So hydrogen is looking for another electron somewhere. I believe this is lithium, but I'm not a chemistry teacher. It's been a while since I've learned all my elements, but I believe this is lithium. So this atom has 3 electrons. So it has 2 in the inner shell and 1 in the outer shell. So it's going to have 3 protons, 3 neutrons, 3 electrons. Well, neither one of these atoms is happy. They both need something. The atom over here needs to give an electron away, gain an electron, I'm sorry. The atom over here needs to give one away. So what do you think is going to happen? So what will happen is this electron will be grabbed up by this atom. So now, after the bonding, it still has 1 proton, it still has 1 neutron, but now it has 2 electrons. So now I have more negatives than I have positive. So this is going to become a negative ion. And what were negative ions called? Anions, A minus. So this is now an anion. So this one is negative, and this one lost an electron. So after it lost an electron, so it had 3 protons, so it still has 3 protons and 3 neutrons, but now it only has 2 electrons. So this one gained the electron, this one lost the electron. When it lost the electron, it lost negativity, so now it's a positive ion, which is called a cation, C+. Now what's going to happen is this negative ion And this positive ion will now stick together because negatives and positives, opposite charges, attract. So that brings us to chemical formulas. Chemical formulas is just a shorthand method for describing what is inside of a molecule. So what atoms are inside the molecule. The structural formula tells how the atoms are arranged. So, for example, the Mickey Mouse look of water. The chemical equation is a way to show the chemical reactions between atoms and molecules. So if you look here, we have 6 molecules of carbon dioxide, 6 molecules of water, and then energy. That's specifically light energy. And it makes C6H12O6 and 6 molecules of oxygen. So if you counted all these atoms up, then there would be 6 carbons. Well, you would have to end with 6 carbons also. Does that make sense? 6 carbons here, so there's 6 carbons here. And if you did that for every atom, you would see that you started with an equal amount that you end with. This is the equation for photosynthesis, which we will learn more about in a different unit. Anyway, so reactants are going to be the things usually to the left of the arrow. So these would be my reactants. They are what you start with. So in a plant, plants take in the carbon dioxide, the water, and the light energy. The products are what's produced. So that's what you end with. And they're usually on the right. So the products of photosynthesis are going to be C6H12O6, which is glucose, sugar, and oxygen, which is released into the atmosphere. So I mentioned earlier that electrons are constantly in motion, and they're in different parts. Because of that, they're in different parts of the molecule at different times. So this causes a positive and negative charge in that atom to constantly kind of move. So these are called van der Waals interactions. So there's 4 main types of basic chemical reactions that are in living cells. So first you have synthesis reactions. So if you recall from learning your prefixes, you'll remember synthesis means to make. So you're making things with synthesis. You can also call this anabolism. Okay, so in anabolism, you take atoms, smaller atoms, to form larger molecules. So you're putting things together. So I take these 2 things and I put them together to get this. So if you look, you're taking 2 smaller things and combining them to form something larger. So anabolism, a lot of people think of anabolic steroids. They build muscle. Those are like the illegal steroids that sometimes professional athletes get caught using illegally because they build muscle, and so they're building muscle, which is actually not good for you. Decomposition reactions are known as catabolism. So catabolism is the opposite of anabolism. So if you're decomposing something, then you're breaking it down. So decomposition reactions are when you take large molecules and you break them into smaller molecules. So they're the opposite of synthesis reactions. So we have a large molecule being broken into 2 smaller molecules. Now, in a reversible reaction, there's one significant way you can look at a reversible reaction. The arrow goes both ways. Okay, so the reaction can go either way. So a lot of the times you have some sort of factor that causes it to move this way or that way. Those factors could be heat, pressure, exposing them to other chemicals or environmental conditions, and those factors are called a catalyst. You know that if you heat things up, like if you heat water up, it's going to help the salt dissolve faster. Or like if you're making sweet tea, then the sugar dissolves faster if the tea is hot rather than if the tea is cold. So those things act like a catalyst to speed up the reaction. So anyway, a reversible reaction, so carbonic acid can form water and carbon dioxide, or water and carbon dioxide can form carbonic acid. It goes both ways. Then an exchange reaction is is going to involve synthesis and decomposition. So the arrow does not go both ways. A lot of people get these two mixed up. So remember, reversible, the arrow goes either way. With exchange, you have both synthesis and decomposition. So what that means is you're going to be making things at the same time you are breaking other things down. Okay, so let's take a look at this reaction. So here I have hydrochloric acid, HCl. So I break down hydrogen and chlorine, and I form water and salt. So I broke this down to form these two things. Same thing with sodium hydroxide. Na is the sodium, OH is the hydroxide. So I broke the sodium apart to make salt, and then the hydroxide to help form the water here. So it's involving both breaking down and making, synthesis and decomposition. Inorganic versus organic molecules. So we're not going to talk a lot about inorganic compounds because this unit is mainly on the biomolecules, organic molecules, but you do need to understand the difference. So inorganic compounds do not contain carbon. So carbon is one of the elements that life centers around. And if you remember, we talked about the four that make up 96%. That's CHON. Carbon is one of those. So this is not made by living organisms. Carbon is not, even though we take it in. We're referring to inorganic compounds here. So you're not going to see these things in, you might take in an inorganic compound, but a non-living thing will be inorganic. So salt, for example, is not alive. Water is inorganic. That's a big one. So we take in water, we require water because we require hydrogen and oxygen, but it is itself inorganic. Metals, gases like oxygen. So we're going to talk a little about water because it is so important. So water is inorganic, so it is not made from carbon or other living things. So water is 1 atom of oxygen, 2 atoms of hydrogen. And we mentioned before that the oxygen and the hydrogen are linked by covalent bonds. But when you have multiple water molecules, see the S for plural, they're linked by hydrogen bonds. So this causes water to heat up and cool down slowly. So basically, water maintains temperature better than most other substances. So that's one reason why your body's made primarily of water, because we need to maintain homeostasis and maintain our temperature. It also stabilizes air temperatures because it absorbs heat or releases heat. And water can absorb and release large amounts of heat with only slightly changing temperature. So it's actually good that we live in a coastal area because living with the higher humidity, it stabilizes our temperature from getting much hotter or much colder, the water in the atmosphere. So water, of course, we know is essential for life. It stores heat efficiently, and it also binds to itself and other things. So the most abundant inorganic thing inside of a cell is water, and I think most people know that. And that percentage depends on how hydrated you are and lots of other factors. But that number tends to be anywhere from 65 to 85% even, and most people are going to be around 75%. As far as their hydration goes. But your hydration can vary from day to day. So again, this is water. So Mickey Mouse's face is negative, right? So we have our negative here, our oxygen, and then our positive hydrogens. So because water is polar, it's a good solvent. That means that it can dissolve lots of things. So that's why we usually use water to dissolve things, because of the positive end on one side and the negative end on the other, it can pull apart other molecules. Now, if the molecule is polar, it will easily pull it apart because it can pull the positive end or the negative end apart. Like salt. Salt has a positive and negative end because it's a ionic bond. Now, nonpolar things are not going to dissolve well in water. So nonpolar things are like fats and oils. So this is why you have to shake up salad dressing, because the salad dressing has oil components and water components. So when you shake it up, it will look like this. It might look mixed, but it's just making the oil droplets or water droplets much smaller. So it seems mixed. So that brings us to organic versus inorganic compounds again. So just reminding you that organic has carbon, usually has hydrogen bonds, but inorganic usually does not have carbon and has hydrogen and does not also have hydrogen bonds. So it lacks carbon and hydrogen bonds. So again, your inorganic compounds are going to be like water, gas, salt, metals. They're usually simpler, and they are not made of carbon and do not come from living things. And remember, water is a great solvent. Now, one thing that inorganic compounds are great for is forming ionic or electrolytic solutions when they're dissolved in water. So in your blood, you actually have electrolytes, which is why if you're dehydrated, you have to replenish those electrolytes. So that's kind of what it's talking about. That's going to be like salts. Anyway, so that brings us to organic compounds, which is pretty much what the rest of these notes are on. So organic compounds are characterized by different forms, and some of those might be isomers, polymers, and we're going to talk about each one of those things. So an isomer is a compound that has the same exact molecular formula, but their structure might be different. So here's one example of an isomer: ethanol and dimethyl ether. They both have 2 carbons and 6 hydrogens and 1 oxygen, but they're arranged differently. We're going to talk about another one in a few minutes. So the functional groups allow synthesis of new molecules by replacing certain hydrogen atoms by other atoms and molecules. So the carbon backbone of organic compounds is usually non-reactive because it is going to be bonded to other atoms and molecules. Polymers are also known as macromolecules. If you remember, poly means many. Okay, so poly means many. So our macromolecules have many small monomers linked together. So the smallest or building block is going to be called a monomer. And remember, mono means one. Okay, so you can think of this like Legos. The monomer is one Lego. That would be my monomer. But the polymer is the whole Lego castle. That would be the polymer. So your polymers are going to be your macromolecules, your carbohydrate, protein, lipid, nucleic acid. And so linking the monomers together is called polymerization, or making polymers is polymerization.